In this video, we're going to talk about some factors of solar electricity that we're going to need for our installation. Again, I'm not an expert. I just did a ton of reading, ton of research. I've gone through, and these are sort of the items that we care about with electricity and how it impacts impacts the installation. So first off, to understand what watt is a unit of power measured as volts times amperage. So really, if you think of watt, it's like the amount of electricity produced. Voltage is the force of electricity, and current, or amperage, it's known by many names, is how much electricity. So an example that a lot of people use when explaining it is water hoses. So if you think of the volume that's in between the pipe, right, of the actual hose, right? If you think that it's the size of a garden hose, right, that's how much, regardless of how much water is going through, that's how much electricity you could have, right? It's the space between the hose. And likewise, in a fire hose, it's a lot bigger, right? So you get a lot more water through. Voltage is the force of which water is coming out of that hose, right? So if you think of a garden hose, again, it's a lot smaller and it trickles through. If you think of a fire hose, it's a ton of force, right? They use it to put out fires. Now, here's the tricky part and here's why this is important and why it's tricky, right? Imagine if you were sending the same force of electricity that a fire hose has out of a garden hose. What do you think is going to happen? It's going to break apart. It's going to rip by the seams. It's not really what you want to do. Nothing good's going to come out of it. Likewise, when you're sizing wiring for your solar panels and electricity coming through, you got to be careful with how big the wire needs to be, right? Depending on how much voltage you're sending through, you need to size your wire accordingly. And there's different metrics. I'm not going to go into the details of it. It's not really necessary. When we actually set up the solar installation at our house and run the wires, I'll go into a little bit more detail about it. But for the purpose of this video and what I want to talk about, it's just to understand the terminology that I'm going to be using. This way I don't have to keep explaining it over and over again. Again, so amperage is how much electricity, so the width of the hose that's traveling with water, and voltage is the force of electricity. And you want to be careful with your sizing that you're not undersizing the wire, because if you undersize the wire, just like you're sending water that comes out of a fire hose through a garden hose, it's going to burn up and you could cause a fire. So you want to make sure you size things appropriately. The other piece that I wanted to talk about is circuit breakers, specifically in the US. I mentioned this in the other video, and I had some questions from the folks that I sent it to, so I'm trying to answer that. Basically, when you send power through the electrical grid, you get 3 wires that are coming into the house. There is a neutral wire. I think this is the neutral wire. And then you have 2 legs, L1 and L2. L1 is 110 volts. L2 is 110 volts. If you combine them together, you get 100 or 240 or 220 to 240 volts. There's a little bit of change. So each side of your electrical panel is fed by a different L1 or L2. So L1 might be on this side, and these plates are hot, meaning they conduct electricity, and these circuit breakers just snap on. So on this side you have 110, on this side you have 110. I think I have a. All right, so if you want to get a device that has 220 volts, um, you have these double breakers, which basically carry the electricity from both sides. So it takes the 110 from here and 110 from here, and you combine it, and you could use it to power some of your bigger appliances. So if you think of a electric dryer or electric stove, you get two two feeds that are combined, and basically that's how you get your 220 volts. Another thing to note here is that the ground, there's usually a bus bar which is all ground. So when you're doing your wiring, in this picture, the ground wires are here on the top area. When you're doing your wiring, you do a positive, you have a positive and a negative side, and then your ground or neutral usually goes to the bus bar up there. And then finally, the other terminology that I want to cover is low frequency and high frequency inverters. Most of the inverters that are plug and play, that are like around 5,000 watts, or 5,000 kilowatts, 5 to 8,000 kilowatts, they're high frequency inverter. They're usually cheaper, they're lighter, but they can't really stand up to higher load, and that's primarily because there's no transformer. Low frequency inverters are much more expensive. They're much more heavier because they actually have a transformer built in, and they could stand up to high load. So if you think of a low frequency inverter, you could go up to 15 kilowatts. Normally at my house, the usage is around 8 to 12 kilowatts, because sometimes you have some surges that are built in. But most houses, if you could get a 15 kilowatt inverter, and that should be good for your whole house. I actually got a 25,000 kilowatt continuous load that can handle surges up to, I don't know, some ridiculous number. I don't need anywhere close to that. But the only reason I got that big of an inverter is just to handle the higher load and not to worry about things burning out. And I didn't want to be shortchange the inverter, so I just spent a little extra money to get the low frequency inverter that was big enough to handle my entire load. So that's basically the terminology I wanted to cover: watts, voltage, amperage or current, circuit breaker wiring, L1, L2, and inverter, high and low frequency. Again, high frequency is cheaper. They're usually I think MPP ones. There's a bunch on the market that are plug and play. They have the charge controller, they have the inverter and the automatic switch all built in. They're usually cheaper. You see them on RV installations a lot. But when you come to home installation, I recommend, based off of all the research I've done, is to get a low frequency inverter that actually has a transformer built in that can handle the higher load. So you don't have to worry about wires burning out, or sending too much load through and burning out fuses and stuff. As I was putting this together, I did realize that I do need to talk about fuses and breaker boxes because of the level of electricity that I'm sending through. But honestly, I don't know enough about it. I'm still researching. If anyone has any insight, please leave it on the comments. I would love to hear what folks have to say. Thank you so much.